Hello and welcome to my YouTube channel. Today, I'm going to continue to solve last year's final examination paper, right? And this is the examination for applied electricity 2024-2025 academic year. Right? Now, let's get started. I've already solved the last 30 questions. That was from question 90 to question 120. Today I'm going to be solving from question 60 to question 90. And these questions, they cover chapter 5, which is capacitors and capacitance. So I'm going to start right away. So starting with question 60. Question 61 rather, right? You have question 61. Find the capacitance to be connected in series with a 10 microfarad capacitor for the equivalent capacitance to be 8,000 nanofarad. So to solve this, the 8,000 nanofarad is, you have to change it to microfarad so that they all be in the same prefix, right? So that would just be what, 8 microfarad. So we are interested in the capacitor to be connected in series with the 10 microfarad capacitor for us to get an equivalent capacitance of 8 microfarad. So to do this, since this is about connection of capacitors in series, so we can just say that the product, right? There are two capacitors, so the product over the sum. So I can write C1, that is the first capacitor. It's in series with the 10 microfarad capacitor, that is just 10 micro, all over the sum. The sum is C1 plus 10 micro, and that will give us 8 micro, right? 8 microfarad. So we have this. Then we make C1 the subject. And what do we get? So we multiply this. So we have yet to be 10 micro C1 will be equals to 8 micro C1 plus 8 times 10, that will be 80. So 80 micro, right? With this, we can send this across, or this will just be what, 2 micro C1, that is equals to 80 micro. So we divide both sides by 2 micro. So the micros go away. So we have 80 divided by 2. Then we end up getting 40. So the answer here will be A. Question 62. When a capacitor is fully charged, the dance is 0. So the current is 0. If you have a capacitor, or in this case, your phone, when it's fully charged, at that instant, the current is 0. When charging a capacitor, the charge increases as the voltage increases. So if you are charging a capacitor, in this case, your phone, right? The charge is going to increase as the voltage will increases. So the answer here is A. A is B. So we have B. A capacitor consisting of 2 metal plates, each of area 240 millimeters square and spaced 220 millimeters apart in air, is connected across a 160 volt supply. Answer from question 64 to 65. So how do so we go to this question. So it should be 66, right? To 66. Now let's go to question the first question, 64, calculate the capacitance of the capacitor. Now this, we have to first write the formula, and the formula for this is capacitance will be equals to, if you can see here, we are dealing with the medium, and the medium that we have here is air. So we use the what? This formula, the capacitance equals to the permeability of free space times area over the distance between the plates, right? When it comes to the permittivity of free space, it's a constant value, which is 8.854 times 10 to the power minus 12, right? Then times, right? You multiply this by area. The area is giving us 240 millimeters square, right? That's the area of one plate. Times 10 to the power minus, so 10. So millimeters square, that will be 10 to the power minus 6, right? So that will be minus 6. Then all over the distance between the plates, 2 millimeters. That is just 20 millimeters. That's 20 times 10 to the power minus 3. So if you do all this, you get the answer to be equals to what? C, which is, right? Which is going to be 0.11 microfarad. Now moving forward to the next question, we have 65. Right, 65. Let me clean this so that you can see. Question 65. Find the energy stored in the capacitor. The energy stored, again, we write the formula for energy stored in a capacitor, which is half capacitance times the voltage square. So the capacitance here, which we just know that is what? C, that is 0.11 picofarad. So that will be half 0.11 times 10 to the power minus 12 times the voltage square. Voltage here is 160 volts. So we have 160 volt square, right? And then this one too, when you solve everything and you express it in micro, you are going to get the answer to be equals to A, right? So this answer will be A. So I have to clean this to get answer here. Will give you A, which is here. Get A. Okay. Question 67. Does capacitor has shorter service life? So here, if you have different kind of, we are giving different kind of capacitors. And if you look at them, the paper capacitor is going to have a shorter service life, because if you are having a paper capacitor, what that means that because the paper can become moist. So if you have a capacitor that is being manufactured using paper, for after some time, the paper will start to deteriorate. So it will get damaged easily. So that means the service life order is going to be what? Very small. So the answer here is C. Two capacitors, 200 microfarad and 150 microfarad are in parallel and then connected in series with 100 microfarad. Determine the equivalent capacitance of the parallel series connection. So here we take this one after the other. We can see here first we have 200 micro and then 150 micro are connected in parallel. So we have to make sure they are in parallel here. So let me bring one of them down so that we have this. So here is 200. After that, in series with what? 100, right? So bring the 100 microfarad here. So we are interested in calculating the equivalent capacitance. Now, how do I do this? We know that if you have two capacitors and they are connected in parallel, the equivalent capacitance for that two will just be the sum. So we have here, the first one will be just 200, meaning be 150 plus 200, that will be 350 microfarad, right? After that, this is in series with what? So you have now 350 microfarad. It's now in series with what? 100 microfarad, right? So we are now interested in the equivalent capacitance for these two, and that would just be what? The product over the sum, since they are just two capacitors connected in series. So that will be equals to 350 micro times 100 micro all over the sum, meaning we have 350 micro plus 100 micro. So that will just be, you do the multiplication here of micro, right? All of it micro. So you have micro square here, micro. So we have 3000, 0. Then you add this other 0 here. Then here we what? 450, right? 450. So this will cancel, leaving only 1 micro. So this cancel. So if you have 9 here, goes here. No, 5 rather. We have 9. And here will be 7. So that would just be what? 700 divided by 9. And that will give us this answer to be 77.78 microfarad. So you bring the micro, so you get this. Now moving forward to 69. The absolute permittivity of a dielectric material is defined as, here we are interested in the, right, the absolute permittivity of a dielectric material. We already know this, right? I'll talk about all this. So if you can just remember the formula, we know that if we are having a material, right, like let's say silicon ion, and we are interested in the absolute permittivity of silicon ion, for example, is going to what? The magnetic flux density over the magnetic field strength will be equal to what? The absolute permeability of the material, right? So let's say this is silicon ion. So if you look at the formula that I've just written here, so you just see which one of them fits the formula that is here. So you can see absolute permittivity of a dielectric material is defined as, it's going to be defined as A, electric field strength divided by electric flux density. Now, electric flux density divided by electric field strength. Electric flux divided by dielectric field. So you can see here is going to be what? B, right? Electric flux density divided by electric field strength. That will give us, right here, okay. And this is about permittivity, or permittivity. So this one will be rather D, right? That would rather be D, electric flux density. So that would be what here will be, right? Electric field strength, that would be E rather. And then here we have permeability or absolute permittivity. So we have this, right? But we see electric flux density divided by electric field strength. So that would be C. Moving on to question 70, right? We have 70. Coulomb's law cannot be used to find the force between two charges. This is going to be false. We know when you talk about Coulomb's law, it's actually used to find the force between two charges. 71. Interleaving 10 plates will result in vast number of capacitors. So if I have 10 plates, right, then you interleave them, that means you get n minus 1 number of capacitors, right? N represent the number of plates. So that will be what? 10 minus 1. That will be 9. So you get 9 capacitors. Capacitors of 3 microfarad, 8 microfarad, and 2 microfarad are connected in parallel. Find the equivalent capacitance. So if they are in parallel, so it just be the sum, right? Since the capacitors are in parallel, it just be the sum. That will be 3 plus 8. That will be 11 plus 2. That will be 13. So the answer here is C. Question 73, right? We have preamble 7. Use figure 2 to answer question 73 to 76. So we have this here, question 76. With this question, right, we have to calculate the equivalent circuit capacitance. So this is a figure 2 that we have here. Here, if we are to calculate the equivalent capacitance, we can see that we have 4.5 microfarad and then 1.5 microfarad. They are what? In parallel. So we can just do the sum. So 4.5 plus 1.5, that will be 6, right? 6 microfarad. After that, you see that it's going to be what? In series with what? 3 microfarad. So to get the equivalent capacitance, that would just be what? For these two, the 3 microfarad and 6 microfarad. That would just be the product over the sum. 3 micro times 6 micro over the sum 3 micro plus what? 6 micro. That will be equals to 18 micro square over 9 micro. So this will cancel. You have micro here. That will be what? 2 micro farad. So the answer here will be 2, and that is C. Question 74. Find the charge on the 3 microfarad in figure 2. So if we go to figure 2 here, we are interested in the what? In the charge. So when it comes to the charge, we already know the equivalent circuit capacitance, which is 2 microfarad. This one here. So to get the charge, we just write here. The charge, since these are what? You see that now that we have 3 microfarad and then 6 microfarad, which will be the equivalent resistance of this one, are now in series, right? So if they are in series, that means the change charge is going to be on them, right? On each of them. So we have here, the charge is going to be equals to the equivalent capacitance times the voltage supply, which is 300. So we have charge on this, meaning on the 3 microfarad will be equals to the equivalent, which is capacitance, which is what? 2 times 10 to the power 2 micro, 2 times 10 to the power minus 6, times the voltage supply, which is 300 volts. So that will be, so here you can see here we have, this will cancel with 2 of this, so that will be 10 to the power minus 4. 2 times 6, 2 times 3, that will be 6. So we have 6 times 3 to the power minus 4. And that will just be 0.6 millicoulombs, right? So we have here to be what? The answer here to be equals to A, right? 64 is A. Determine the voltage across the 1.5 microfarad in figure 2. So figure 2, we are interested in the voltage across this, right? The voltage. So now, you can see that 4.5 microfarad and then 1.5 microfarad are in parallel. So what that means that since they are in parallel, we know that for parallel connection, that means the elements, they have the same voltage on them, right? So the voltage across this 1.5 micro is the same as that of 4.5 micro. And it also is the same as what the voltage across the 6 microfarad here. So to get the voltage, we can just get the voltage by what? By using this formula. We know charge, right? We know charge is equals to a capacitance over voltage. So if I'm interested in the voltage across 6 microfarad, which is just going to be the same as the voltage across 1.5 microfarad here. So that will be equals to what? The charge on it, and the charge on the 6 microfarad, we already know that is what? 0.6, right? Let me write this clearly here. So we have this here. That is just going to be equal to the voltage across the 1.5 micro will equals to the voltage across the 6 micro farad, right? And that is going to be equal to what? The charge on it over what? Charge over what? Its capacitance, right? That is 6 micro, right? So now I can write the voltage across the 1.5 microfarad to be equals to the charge. We know the charge, which we calculate to what? 6 milli, 0.6 millicoulomb. So 0.6 times 10 power minus 3 over the capacitance, which is 6. So we have here 6 micro, right? 6 times 10 power minus 6. So we can see here with this here, if this is the 3 to the power minus 3, so this will cancel. So you take the 10 to the power minus 6, you take it up, you get 10 to the power 3, right? Because we'll cancel this. Then we have 0.6 over 6. So that 0.6 just 6 times 10 to the power minus 1. So we have here times 10 to the power minus 1. So we have 6, right? 6 over 6, that will be 1. So 1 times this, right? So that will just be what? 100. So the answer here will be D, 100, right? We get here 100. So this is one way of doing it. If you don't want it to do it this way, you can even get the same answer, right? By using the what? The voltage divider rule, right? Voltage divider rule. And that simply is going to be equals to, if I'm interested in the voltage across the 6 microfarad, which is going to be the same as the voltage across the 1.5 microfarad, I can just do this, right? 1.5 microfarad, right? The voltage across it will be equals to, again, right? That will be equals to, if I can see, you can see here the equivalent capacitance, which was 2 micro, right? So 2 times the power minus 6 over the what? This thing that we are interested in, which is 6 micro, the capacitance, 6 power minus 6 times what? 300, right? Times the voltage supply. So when you do this again, see that here will just be what? This and this will cancel. You have 1 over 3 and 300. So that will be 100 volts as well. So you can do it this way too. The type of capacitor depends on the type of dielectric material. This is true, right? Because if you have a capacitor, you have a dielectric material between the 2 plates of the capacitor. So that depends the type of what capacitor. So that's why we have paper capacitor, plastic, ceramic, and then mica, right? The charge stored in a capacitor depends on the area, plate area, and dielectric. B, microstructure of electrode and electrolyte. C, thermodynamics and mass. And so the answer here will be A. We know that if I have a charge, right? If I have, for example, a charge, and charge is just equals to capacitance times what? Voltage. We know capacitance, what? The area of what the plate is very important. Then also it's between the plates, then times it. So this is A. When a capacitor are connected in parallel, that remains the same, and then dash varies. So if you have capacitor, they are connected in parallel, we know that the voltage is going to be what? The same, but the charges vary. So voltage is the same, charge varies. So B. 3 50 microfarad capacitors are connected in series across a 250 supply. Find the charge on each capacitor. So here we are dealing with 3 50 microfarad capacitors. So we have 50 microfarad capacitor, right? Right. So these capacitors that we have there, they are the same. Each capacitor is 50 microfarad, and we have 3 of them, right? Now, here we have to find the charge on each capacitor. So here, to find the charge, we have to get the equivalent capacitance. And the equivalent capacitance, since these are identical, so the capacitors are identical, I can just write the equivalent capacitance will be equals to the number, the capacitance, which is 15 micro, over the number of capacitors, 3. So that will be 15 divided by 3. That will give me 5 microfarad. That will be the equivalent capacitance. Now, when it comes to the charge, these are connected in series, right? And we just calculate the equivalent capacitance. So the charge will equal to, meaning on each of the 15 microfarad capacitor equals to what? The equivalent capacitance times the voltage supply, which is 250. So I have 5 micro times 250. And that is going to be equals to, here we have, okay, we can write here 0, 5 times 25. I think that is going to be equals to 125, right? So 125 times 10 power minus 6, right? So if we're to do this, right, I can express this in milli, right? So in milli, that will be 1, 2, 3. So 1.25 millicoulombs. So the answer here is D, right? The answer, okay, it's not this one, rather. I'm circling the wrong way. So it's A here. The wrong question. That is A, right? And you can see that that's one way of doing it, right? One way is you can find the voltage, right? Because if these are 3 capacitors that are connected, right, they are identical, meaning they have the same capacitance. That means the voltage is going to be the same. And then also the charge on each of them is also the same because they are in series. So we can even get the voltage across each of these 3 capacitors that are connected in series. And that would just be 250 over 3, right? 250 over 3. And from there, we can go and get the charge. Now, for how long must a charging current of 2 amps be fed to a 10 microfarad capacitor to raise the potential difference between each place by 600 volts? So here we are interested in the time, right? So if I have a current of 2 amps be fed to this. So here, to do this first, we have to get the charge, right? Because if we are dealing with a capacitor, and this capacitor is 10 microfarad, and the voltage across is 600. So I can get the charge. Charge is going to equal to what? Capacitance times voltage, right? So charge here will be equals to, the capacitance here is 10 micro, 10 times 10 power, 10 times 10 to the power minus 6, times the voltage, which is 600. So what do I get? The charge here will be equals to 6 times this. That will be what? So we just have 600. That will be 6,000 times 10 to the power minus 6. So that will just 6 millicoulombs. Now, we are interested in the time. We know also that when it comes to current, right? Because we are giving the value for current, which is 2 amps. And when it comes to current is equals to charge over time in the flow of charges. So I'm interested in time. We make time the subject. That will be equals to charge over current. So the charge is now 6 milli, 6 times 10 to the power minus 3 over the current, which is what? 2, right? So on this, we just get 3 milliseconds. So the answer here we what? C, 3 milliseconds. Question 82. In figure 3, capacitors Q and R are identical, and the total equivalent capacitance of the circuit is 5 picofarad. Determine the value of Q. So here, how we just be calculating the equivalent capacitance. And when the last equivalent capacitance that we are going to get, that represents the overall equivalent capacitance. And that will be equals to what? The 5 picofarad here. So let's start with it. So the first part here, 5.5 picofarad and 2.5 picofarad are in parallel. So here will just be the sum, and that will just be what? 5.5 plus 2.5, that will be 8, right? 8 picofarad. Then when it comes to here, this 8, 2 and 8 pico will now be in series. So here to get the equivalent capacitance, that will be equals to what? Right? For the 2 and then 8, right? That will be equals to the product 2 times 8. Remember, they are all pico. So there's no need to even put the pico here. If I just leave it like this, over the sum 2 plus 8, right? That will be equals to what? 16, right? 16 over 10, that will be what? 1.6 pico. So you can just do it this way. When you finish, you bring the pico, we add the pico. Now, that is for the whole of this, right? The equivalent capacitance for this part, the top part that we have here. Now the bottom, right? So when you come to here, the bottom, we have to get that place, the equivalent capacitance. And we have been told that Q and R are identical. So if they are identical, we can easily get the equivalent capacitance. And they are connected in series, right? So since they are in series, that will be equals to what? I can take only Q, which represents the capacitance. That will just what? Q over what? 2, right? They are identical. Now, with this, you can see the top part, which we got the equivalent capacitance with 1.6 pico, is now in parallel with what? The equivalent capacitance, which is, right, the capacitance over 2 here, the Q over. So the sum will give us the 5 picofarad. So I can just write here 1.6 plus Q over 2 will be equals to what? 8. A will be equals to what? The equivalent capacitance, which is what? 5 pico, right? So you just make Q here the subject, that will be equals to, multiply this by 2. So we have here 2 times 1.6. Multiply 2 times 1.6. 1.6. So you get 3.2, right? So 3.2 plus Q equals what? 2 times that will be 10. So charge here will be equals to 10 minus 3.2, and that will be equals to what? 6.8 picofarad. So the answer here will be D. Now question 83. A capacitor consists of 2 parallel plates, each of effective area 50 centimeters square, has capacitance of 1000 picofarad with a dielectric of thickness 0.4 millimeters. What is the relative permittivity of the dielectric? So here, relative permittivity of the dielectric. Okay. So here, first, we are giving the what? A capacitor, right? We are giving the what? The effective area, right? So here is the formula, right? Because now we have a dielectric material. We just write this capacitance is equals to what? The absolute permittivity of the dielectric material. And that equals what? Permittivity of free space times the relative permittivity of the material times the area over the what? the distance between the plate, which will be the thickness of what the dielectric material, that will be D. So we make relative permittivity the subjects, and what do we get? That will be equals to, right? We have this over CD over, so that will now be what this over area, right? So we do all this, and what do I get here? So we get the relative permittivity here to be equals to capacitance is what 1 picofarad. 1,000 picofarad. That's just what 1 microfarad. So that's just 1 times 10 power minus 6 times distance between the plates 0.4 millimeters. So that's 0.4 times 10 power minus 3. Then we have the permittivity of free space, that is 8.854 times 10 power minus 12 times the area, which is 50 centimeters squared. That will be equals to 50 times 10 power minus 4. Right? So we have all this. If we do all this, right? So what do I get? Here, we try and do it. We know here 10 to the power, there with minus 9, right? So the whole of this on top is 10 to the power minus 9. Then I have 1 here, right? So here is 0.4. So 0.4 is just 4 times 10 to the power minus 1. So here would rather be 10. And then we have 1, right? So minus 10 on top. Now the bottom we have what? 10 raised to the power, right? 10 raised to the power minus 12 plus minus minus 4. But here there's already 50 here. So this will cancel. Here will be minus 3. So that will be minus 15, right? Minus 15 here. 5 times 8.5. So we have 8.854. 8.854 times 5. And that will give us this, right? So if we have this, right, we take inverse of this. Where's inverse? Inverse of this. Okay. So we have 44.27. Okay. 44.27 inverse. So we have this, right? So we have 0.22. Okay, so here the answer is going to be equals to, right? Okay, and then we have 4, right? So this times 4. So the whole of this times 4. That is 0.9. So 0.9. Okay. 0.9. 0.0903. Or I can say 0.4. That's 10 to the power minus 10, right? Minus 10 over here 10 to the power minus 15. Okay. So if we have this, so, and we can express this in what? So what do we get? 1, 2. So if we have this here, all right. Okay. So if we have this, so we should end up getting something like D, right? The answer here should be equals to D, right? So be equals to D. Now, moving forward, right? We look at, right? We look at Question 84. Find the voltage across a capacitor when the charge on it is 4 millicoulombs. So we are interested in the voltage, right? So here we have voltage. Now voltage is equals to what? Charge over capacitance. So we are interested in the voltage. Charge is what? 4 milli, right? Then the charge capacitance is 20 micro, 20 times 10 power minus 6. So what do we get? Here will be 10 to the power 3 for this. Then we just have 4, right? So here will be 1, here will be 5. So we have 0.2 times what? 1000. That just be what? 200. So the answer here is 200 volts. A capacitor uses a dielectric 0.04 millimeters thick and operate at 300 kilovolts. What is the electric field? So if we have this here, right? We are interested. What is the electric field strength across the dielectric at this voltage? Here again, you have to try and remember the formula for the electric field strength. That is what, in terms of the voltage across a capacitor and then the distance between the plate of the capacitor. That will be equals to what? Voltage over distance, right? So here the dielectric will just be equals to, right? We have 300 times 8 power 3 all over 0.04 millimeters. So 0.04 times 8 power minus 3. So here with this will be equals to, you bring this up, that will be 10 to the power 6, right? But even before that, 1, 2, 4 here we just what? It will just be 4 times 8 power minus 2, right? 1, 2, right? Minus 2. So here will rather be 5 initially. So when you bring, you get 8. So this will rather be 8. This will 10 to the power 8 here. And we have here 300, right? That will be 300. Now divided by 4. 300 divided by 4. Divided by 4. That will be 75. So you can see here the answer here can be 7 point, right? 7.9 giga, right? So you write 7.5 rather giga. Okay, where is it? Gigavolts per meter, right? So this question was given as a bonus, right? Because the answer is not there, right? Because all this are kilo, even though this is right. Yes, the mega doesn't, it's really mega to not be, if it's mega, you have to what? 7,500. So here was given as bonus, right? Bonus, the answer is not there. How many plates has a parallel plate capacitor having a capacitance of 5 nanofarad? If each plate is 40 millimeters by 40 millimeters and each dielectric is 0.51 millimeters thick with a relative permittivity of 6. So here we are just interested in the number of plates. This is example that we solve during lectures. So here we just write the formula, right? So we have this here. We just make the relative permittivity. We are interested in the number of plates, right? So here we use a general formula. Capacitance equals to permittivity of free space and relative permittivity times area times the number of plates, which is n minus 1, all over the distance between the plates. So we enter the number of plates, we make this the subject. That will be what? N minus 1 will be equals to, right? CD here over relative permittivity of free space times relative permittivity times area. So we write this. So I have n minus 1 will be equals to the capacitance is given, right? 5 nano, 5 times 10 to the power minus 9. The distance between the plates 0.051 times 10 to the power minus 3 over permittivity of free space 8.854 times 10 to the power minus 12 times relative permittivity, which is also given as 6, times the what? Here at area, right? The area here, they are the same, right? So here, area will be what? 40 millimeters by 40 millimeters. That's just 40 times 10 to the power 3 minus 3 times another 40 times 10 to the power minus 3. So we have all this here. And we have this, right? So if you solve all this, what should we get? Wow. So here will really take some time, but let me try and do it and see. We can get here to be 51, 1, 2, 3, right? 51 times 8 power minus 3 here, right? So that the top part I can have what? Minus 9. Here what? Minus 10 to the power minus 15, right? For the top, right? So you have 51 here. Then the denominator in the bottom side, we can have what? Here will just be 10 raised power minus 6, right? And then 2 of this will go, so 10 raised power minus 4. 4 times 4 will just be what? 16. So here, then we have 6 times 6. Then times what? This one, 10 raised power minus 12, as it that will be what? 16. So we just have 8.854, right? Then here, then I have my 5 times what? 51. Okay. So we have this. I can take 8.854 times 6 times 16, right? So we get this answer. Inverse. So we have this answer, which is 849.984. Okay. Inverse of this. 849.984. Wow. Inverse. So times 5 times 51. So which is what? 0.3, right? So we have 0.3. So somewhere we should be getting 3, right? And then if you look at then 3 plus that will be 4. So the answer here should be what? 4, right? So here all of this we should get 3. N minus 1, that will be N. 3 plus 1, that will be 4. So the answer here will be 4, right? Now question 87. The electric flux density between two plates separated by a maker of relative permittivity 5 is 4 microcoulombs per meter square. Find the potential gradient between the plates. So potential gradient is the same as the electric field strength, right? So we have electric field strength being the same as the potential gradient. So with this question, you can see that we are given the permittivity, right? And then we are also giving here the listen, right? We are giving uh we are giving the um electric flux density. So electric flux density here is 4 microcoulombs per meter square. All right. So I'm interested in the potential gradient. We know that is the electric field strength between the plates, and that is equals to, can write this over, E will give us what? The permittivity, absolute permittivity, which is relative permittivity times permittivity of free space. So if we are interested in this, so we make it the subject, right? So we have this to be equals to absolute permittivity over what? It's rather the opposite, right? To rather be this electric flux density over. This is what? 4 times 10 power minus 6 over, this is a constant, right? 8.854 times 10 power minus 12 times the relative permittivity, which is 5, right? So we have here 5. So with this, we can just do this, right? Let's solve this one first. That will be 8.854 times 5. That is this. You get 44. Right. You get the inverse? No. 44. I don't know why I'm getting this. 44.27 inverse. Okay. Times 4. So we have times 4, and that is 0.09. Okay, this is question 87. Right. Okay. 0.0. So we get here to be 0.0903, right? So get something like this. And then we deal with what? This thing. So here 10 raised power minus 6 goes up 10 raised power 6. So this times 10 to the minus 6, right? And that will be equals to so if we are doing this, so here because what? 1, 2, 3, that will be 90.3 kilovolts per meter. So it will be what? 90.4. Answer here is this. Okay. Now we move to the next question, which is 88. Increasing the distance between the plates, right? We have 88. Increasing the distance between two parallel plates, that's the capacitance. If you are increasing the distance between the plates, that means the capacitance is going to reduce because of the formula, right? If we have, capacitance is equals to this formula, absolute permittivity times area over what? The distance between the plate. So if we are increasing the distance between the plate, that means the capacitance here will decrease. So it's A. The connection of two parallel plates where voltage results in the buildup of charges across the plate. This is true, right? If you connect, you have, for example, right, you have a capacitor and you connect this capacitor to a voltage source, right? Because this is disconnected, then you have charges on the plate. That is a buildup of charges. So this is true. The force exerted on 1 coulomb of charge is called the electric field intensity, right? So it's this electric field intensity. So we come to the end of today's solution. See you in the next solutions. Bye bye.